Hi folks, welcome to this recap of Stats and Probability for IB's Math Analysis and Approaches Standard Level course. This presentation isn't produced or endorsed by IBO, it's just one that I made for my students in PEI Canada. It's not an exhaustive list of statistics and probability topics, just an overview of some of the key concepts. One of the best ways to get the most out of the presentation is probably to pause the video and try the questions yourself. There are timestamps and downloadable notes in the video description, and there are also some accessibility features that you can make use of in YouTube. There are often a lot of different ways to solve a problem, so don't feel like the way that I'm doing it is the way that you have to do it. If you have a different, valid way that you're comfortable with, please continue doing that. Okay, here we go. In stats and probability, we'll have to work with frequency tables, diagrams, and box and whisker plots. So if we have this box and whisker plot here, what is it telling us? Well, it's telling us that the minimum value is 13, that the maximum value is 59, and then it tells us that middle one right here, that's the median, is 32. The first quartile is 25, and the third quartile is 47. From that, we can figure out the range, which is just max minus min, so that would be 59 minus 13, or the range would be 46. And we can also find the interquartile range, which is just Q3 minus Q1. So for us, that would be 47 minus 25, or 22. The interquartile range tells us where the middle 50% of the data lies. So the middle 50% of scores are going to be between 25 and 47. It also helps us define outliers. So outliers are either 1.5 IQRs above Q3, or on the lower side, 1.5 IQRs below Q1. So let's just find the upper boundary. The boundary for the, quote, upper outlier would be Q3 plus 1.5 times the interquartile range, or 47 plus 1.5 times 22. Okay. Now 1.5 times 22 is 33, plus 47, that's 80. What that's telling us is that scores above 80 could be considered outliers. And so if we had a score like 85, it would be represented with an asterisk on the box and whisker plot. Next, let's move along to cumulative frequency graphs and frequency tables. So we've got the lifespans of 200 pet goldfish, and they're represented in this frequency table. And I see I've got 40 of them, and 77, and 28 are between 3 and 4 years old, and 7 are between 4 and 5 years old. There's a missing one, though. Now, if I add up all the numbers that I've got so far here, 40 plus 77 plus 28 plus 7, I could pause and try that, but that would mean I have 152. What I'm missing is 48, because we know this should add up to 200. Once we know that, we can complete the cumulative frequency table. So the cumulative frequency table is asking, how many fish are up to 1 year old? And the answer to that would be 40. And then this part right here is saying, how many are up to 2 years old? So that would be 40 plus 77. Add those together and we'd get 117. Up to 3 years old? Well, you could add all three of these together, or you could just say, it's these 117 plus the new 48. That would give us 165. Okay. Similarly, up to 4 years old, well, let's just add on these 28 more, and that would give us 193. And then for the cumulative frequency, it should end up with 200 of them are up to 5 years old. The next thing we're asked to do is find the mean age of goldfish in this group. So we're going to do this in our GDC. One of the problems is we don't actually know the age of any particular goldfish. All we know is that 40 of them are between 0 and 1 years old. So what we will do is we will take the midpoint of that interval, which would be 0.5. We'll take the midpoint of this interval, which is 1.5. So we're making an assumption here to end up with an estimate of the mean. We're saying that all of those first 40 have an average age of 0.5. And then we head to the GDC. I press Stat, Enter to get into my lists. I'm going to clear anything out that I already have in here, and I'm going to enter this information. So I'll put the ages in the first list, and I'll put the frequencies in the second list. I'm not doing cumulative frequencies here because I want the frequency of each individual sort of grade or age boundary. Once I've got it all in, I'll press second mode to quit, and then I hit stat again and head over to calc. And I'm doing one variable statistic, so I hit enter, and I tell it that the x values are in list 1, the frequency is list 2, so I press second 2, and it can just calculate it for me. It tells me x bar, or the mean, is 1.925. It tells me that the standard deviation is 1.07, and that would be the Greek sigma there, lowercase sigma. And we're going to be using the population parameters in Math AASL. Now that we have those values, we can move on to looking at the cumulative frequency. So chances are on your exam they'll already give you one of these graphs, but we can generate it ourselves. We can say up to 1 year old, yeah, there are 40. Up to 2 years old, there are 117. Up to 3 years old, there's 165. Up to 4 years old, there's 193. And then here we are at the top. And I'll just try and connect these as smoothly as I can. And it asks us to estimate the median lifespan of a goldfish. So we've got 200 goldfish. We're kind of thinking, what's going on with the 100th goldfish? What is its age? So I can just sort of draw across here, and I'm going to have to estimate, but I think it's about 1.8 years. Lastly, it's asking us the question, a goldfish is considered mature if it is more than 2 years old. A goldfish is selected at random, find the probability that it's mature. So how many goldfish are more than 2 years old? Well, let's take a look up here. There are these 48, these 28, and these 7. So that's how many are more than 2 years old, and that is out of 200. So at its basic core, probability is number of events that satisfy the condition out of number of total possible events. In this case, that means 83 goldfish are mature out of 200. Let's move along to some descriptive statistics. Mean is just the sum of the data divided by the number of pieces of data. Median's the middle value when data is arranged either in ascending or descending order, but typically it's in ascending or getting bigger order. If there's an even number of values, you take the average of the middle two. And mode is the most frequently occurring value. There may be more than one of those. Standard deviation is a measure of how spread out the data is, or the dispersion. Larger values mean more variation in the data. And variance is the square of standard deviations. So we ended up with standard deviation and mean for a set of data over here where we had a frequency table. The other situation you might have is where you have just some raw data and you have to find the descriptive stats for it. So let's look at that over here. We've got just some numbers and we want to find mean and standard deviation, say. I'll hit stat, I'll go to my lists, I'll clear out everything by going to the list heading and hitting clear, enter. Next, I'll put in that data. If you wanted to keep all of the data and just use, say, a third list, that's okay too. You just have to remember to tell your calculator that when you're calculating the statistics. So now I'm going to hit second mode to quit, and then it's stat, over to calculate, and again it's one variable statistics. The list is L1. This time there is no frequency list though. So I'm just going to leave that blank, and I hit calculate. And it tells me that the mean is 7.75. The standard deviation is 1.27. I'm going to leave it to a bunch of decimal places, though typically for the IB we're giving 3 sig figs. If I wanted the variance, that is sigma squared, I would take that 1.27475 and I would square it. Okay? And I'd get 1.62. One type of question that the IB loves to ask is, what happens if you say add 2 to each of these values? Now, you can do this by actually doing it to the values and checking it out in your GDC. But adding 2 is going to add 2 to your mean, but it's going to do nothing to the spread of the data. So it will still be 1.27. The next question we get is, what happens to the mean if we multiply each value by 5? So that's going to do just what we expect to the mean. It'll be 5 times our old mean, which is 7.75. And if we multiply those out, we're going to get 38.75. And it's also going to multiply your spread by 5, or your standard deviation by 5. And this is why I'm keeping some extra numbers here. When I multiply by 5, I'm going to get 6.37. Might have had a little bit of a rounding error if I hadn't have kept 3 sig figs. Not a big deal, though, either way. So adding numbers to the data affects the mean, but it does not affect the standard deviation. Multiplying affects both the mean and the standard deviation. Now that we've dealt with some descriptive stats, let's take a look at probability. So we're going to run into this terminology a lot. A union B, the union of the sets A and B. It can be interpreted as A or B or both, so that U kind of means A or B, but it's the Boolean or, which means one thing or the other or both. So in this kind of or, if you say, I want tea or coffee, that means you'd be happy if you got tea, you'd be happy if you got just coffee, or you'd be happy if you got both. It represents this whole area in the Venn diagram, both circles. The intersection of sets A and B can be interpreted as and. So this is A and B. So if I ask for tea and coffee, I want them both, where it's this area of the Venn diagrams. PA with the line B, it reads the probability of event A given that B happened, or given that B is a condition. And then we end up with this wildly helpful formula. And it's one that will probably come up somewhere on the exam. Lastly, complementary events. So complementary events are sort of opposite events. If the event A is being late for school, then its complement, which we call A prime, is not being late for school. And the probability of an event happening plus the probability of it not happening always adds to 1. Let's think about that. If the probability that you're late for school is 0.7, then the probability that you're not late is 0.3, and those two things add to 1. Moving on to some more terminology. We're looking at mutually exclusive and not mutually exclusive events. So if events are mutually exclusive, they cannot occur simultaneously. Think about it. If you're dating someone exclusively, it's only that one person. So consider a deck of cards where A is drawing a club and B is drawing a red card. So there are 13 clubs in the deck, there are 26 red cards, but there are no red clubs. In a single draw, these events are mutually exclusive. A card cannot be both a club and red. So for mutually exclusive events, the probability of having both at once is 0. That's their real definition. And this is a combined events formula that you can use. So let's think about that. Probability that a card is a club or red would be the probability that it's a club, and I'm doing my best to draw a club there, plus the probability that it's red. There are 13 out of 52 cards that are clubs. There are 26 out of 52 that are red, so this is 39 out of 52. A really good way to think about these situations is with a Venn diagram. In mutually exclusive events, that Venn diagram is going to have circles that are disjoint, that do not touch. There are 26 red cards, that was event B, and there are 13 clubs, that was event A. So you can see right here, there's 39 out of 52, because there are 13 that are neither red nor clubs. The less formally that you can do any of these questions, frankly, typically, usually the better. What you should not do is assume that things are mutually exclusive. So non-mutually exclusive events are events that can occur simultaneously. Consider a deck of cards where C is drawing a heart and D is drawing a queen. So let's call this event H and Q. In a single draw, these events are not mutually exclusive because you could have a card that is both a queen and a heart. Honestly, maybe we should start with the Venn diagram here. We've got hearts, we've got queens. We've got one card that is both a queen and a heart. We've got 3 other queens, and we've got 12 other hearts. Now, the IB is not going to set questions that are specifically about a standard deck of cards. It's too culturally specific, but it often comes up in probability in North America at the very least. And that means there are 36 cards that are neither. Right from that Venn diagram, I can find out that the probability that it's a heart or a queen is these 16 cards that are in here. 16 out of 52. But there's also a formula that lets us compute this one here. And this is a great formula because it is always true. If you're not sure about exclusivity, use this formula. So if we were to use this formula to do this one, hearts or queen, we'd say probability of hearts plus probability of queen minus the probability that it is both heart and queen. In terms of numbers, there are 13 out of 52 that are hearts, there are 4 out of 52 that are queens, and the reason we have to subtract off is that we have double counted the queen of hearts, the one that's both a queen and a heart. It's not that we shouldn't include it, it's that we've included it twice. So again, whether you want to do that with a Venn diagram or by thinking about the formula is up to you, but don't assume exclusivity. Another way of classifying events is as either independent or dependent pairs of events. So independent pairs of events are ones where the outcome of one event does not affect the probability of the other. They're independent of each other. So let's classify these pairs of events. Tossing a coin and rolling a die. Does getting a head on a coin make a difference to what you're going to get when you roll a die? No, it makes no difference. So these are independent. Drawing 2 clubs from a deck without replacement. So when you draw that first club, it changes the number of cards in the deck and the number of clubs that are left. It changes your probability of getting a second club. These would be dependent. If events are independent, you can use this handy-dandy little formula, but don't assume independence. I know it's in the formula booklet. There's going to be a formula in there that tells you the probability A and B for independent events. We're going to be tempted to use it anytime we see P, A, and B. Only use it if you're sure the events are independent. So, for example, if I were flipping a coin and tossing a die, what's the probability of getting a head and rolling a 4, let's say? Well, probability of getting a head is 1 out of 2. Probability of getting a 4 is 1 out of 6 on a standard die. There we go. That's a fair way to use this formula. In the other situation, we have to do a little bit more thinking. Conditional probability involves dependent events, typically, and often given that statement, or rather it's needed if we have dependent events. It can also be rearranged for a generally true statement about P, A, and B, that it's PB times PA given that B, or you can switch those A's and B's up. But it's most useful in this form. So that brings us to the question, how do we determine whether 2 events are independent mathematically? Events are considered independent if you can show that the probability of A is the same as the probability of A given that B happened. That means that A doesn't care about B. If probability of A generally is the same as probability of A when B happens, they're independent of each other. You could also show that PA is equal to probability of A given that B didn't happen, or similar kind of statements. Now that we have some definitions, Let's go ahead and do some practice problems around working with Venn diagrams and tree diagrams. So we're looking at a situation where there are 82 students in grade 12 at a school, 64 take math, 56 take Spanish, and 12 do not take either. When you're filling out a Venn diagram, as much as possible, try and start with the middle, if it's at all possible. So in this one, we've got 64 students take math, and 56 take Spanish. This isn't a great way to fill this out. And 12 don't take either. I actually know exactly where those 12 go. Here I couldn't start with the middle because I didn't know it. You can do some algebraic stuff to figure out how this works. But in these situations where they tell you the outside or the people who don't take either, one of the easiest ways to do it is to just add up all the numbers in after we did this poorly. Like I put 64 people in that math circle and 56 in the Spanish, but I actually don't know how they're divvied up between people who take both. If I add all those together, I have 132 people, 64 plus 56 plus 12. I'm only supposed to have 82, so I'm over by 50, And that, it turns out, is the number that should go in the middle. So I'm going to go ahead and fix this up. 50 take both, and so that means 6 take only Spanish, and 14 take only math. Let's see if that all adds up. I've got 14 plus 50 is 64, plus 6 is 70, plus 12 is 82. Glorious. How many people take both math and Spanish? Now, we can show the nice notation here, or we can just write the number. It's going to be that 50 in the middle. Given that a student takes math, what's the probability that he or she does not take Spanish? Oh my. So we're going to do this two ways. We're going to do it with the formula that is right here, and then we're going to do it informally. And generally, if you're able to think it through informally, that's probably at least as good. So this is the probability that they don't take Spanish given that they take math. And that's going to be the probability of both those things over the probability of math. Now, where are the no Spanish and math people? Well, that would be these people right here. So not Spanish and math would be 14 out of 82. Let's take a look at the bottom. Probability of taking math, that actually we know right from the start. There are 64 that take math out of 82. Now I've got fractions to divide, so I just flip and multiply. And I can get this down to 14 out of 64, or if I want to, 7 out of 32, though it's fine to leave it as 14 out of 64. There's doing it with the formula. The other way to think about it is like this. The question's really asking, out of, let's call them the mathies, the people who take math, so out of those 64 people, how many don't take Spanish? Oh, 14 out of those 64 people don't take Spanish. And that's the whole question hacked. Lastly, we're supposed to show that M and S are not independent. So probability of math, we'll do it one way here and then show you another sort of maybe slicker hack. But the probability of math is 64 out of 82. Okay. The probability of math given Spanish is 50. 50 people take math out of the 56 people who take Spanish. And those two things are not equal to each other. All you have to do is check PM and PM given S. An alternate way we could have done this is we already knew probability no Spanish given math is 14 out of 64. We could have compared that with the probability of just no Spanish. And we know 56 people took Spanish. So how many people didn't take Spanish? Well, 26 out of 82. And those two things are not equal to each other. So two different ways we could show it here. But clearly these two variables are associated with each other. That's not to say that taking math causes you to take Spanish. but they're not independent in this case. One last way you could check is just to see if the independent events multiplication formula works, which it does not here. When we have compound events or multiple events happening sequentially, one after the other, often a tree diagram is a nice way to represent both the events and their probabilities. So let's look at an example of that here, again with a standard deck of cards that has 52 cards. 4 of these cards are aces. A student selects a card at random, records whether or not it's an ace. Without replacing the first card, the student selects a second card and records whether it's an ace. So there's a 1 in 13 chance that the first one is an ace, and then we can just follow this tree diagram through. If the first one was an ace, we're down to 3 aces left out of 51 cards now. Okay. On the other hand, if the first card is not an ace, 12 out over 13, then we have all 4 aces left out of 51. And if the first card is not an ace, then we used to have 48 non-aces. Now we're down to 47 out of 51 cards. If we want to find the probability of each sort of branch of the tree, following it all the way through, then we multiply through. So this right here is going to be 3 over 51 times 1 over 13, or 3 out of 663. That's your chances of getting 2 aces. This one right here will be 1/13 times 48 out of 51. Okay, so that will give us 48 out of 663. The next one will be 12/13 times 4 out of 51, which also works out to be 48 out of 663, 48. And lastly, we'd have 12 over 13 times 47 over 51. And we grab our calculator to do these, but that would be 564 over 663. Now, if you added up all these probabilities, guess what? You'd get 1. This is all the possible things that could happen, so a probability distribution always adds up to 1. What's the probability of drawing no aces? Well, that's easy. We just follow that branch through. It's right here. It's 564 out of 663. You can give it as a decimal to 3 sig figs if you like. What's the probability of drawing exactly 1 ace? So that happens in this branch and also in this branch. So it's these two things. It's one of those things or the other. And typically, in counting or probability, when we have an or situation, we're adding. Okay? And often means multiply. So if I add those up, I would get 96 over, make sure you keep those denominators the same, 96 out of 663. Now, the last question, we can do it with our formula. It's got a given that statement. So given that the first card is an ace, what's the probability that the second card is an ace? And in the absence of any other sort of insight, we're going to trust our mechanics here. The fact that we could just use that little formula, ace 2 and ace 1, all over the probability of ace 1. And check it out. Probability that they're both aces? Well, that would be the very top there, 3 out of 663. Probability that the first one is an ace? Well, that's actually right here, 1 out of 13. And I can flip and multiply, or I can do it in my calculator. It's up to you. Which is 39 out of 663. You can also reduce that down, though you don't have to. It's also 3 out of 51, or 1 out of 17. So, works out nicely. I guess the question is, would we be able to do it intuitively, too? Given that the first card is an ace, so we're already on this branch right here, what's the probability that the second card is an ace? It's actually just this 3 over 51. So we could hack the question that way by thinking about what it's really asking. Either way is fine, though. And again, that could be equal to 1 over 17. The IB doesn't tend to care a whole lot about you reducing your fractions unless it turns into whole numbers, but they do not want to see decimals in fractions. The next topic we'll take a look at is binomial probability distributions. So binomial probability functions are used when you have a single event that's repeated multiple times and there are only two outcomes, or you can define it as two outcomes. So if you were thinking about rolling a die, it's true that there are 6 sides, but you might define success as rolling a 6, and then failure would be the other 5 sides. In these situations, each repetition is independent. We'll typically be using our calculators for these questions. The notation for binomial probability distributions is this: x tilde b, and we'd say n, where n is the number of events, and p is the probability of success for any given event. So in context, Ian often has coffee in class. True story. Each day there is a 91% chance he will bring coffee. What's the probability that he'll have coffee exactly 3 classes this week? So assume that we're talking about a 5-day week here, 5-day work week. This would be a situation where we have x is a binomial with probability distribution with 5 events and a probability of success of 0.91 for each of those events. What's the probability he'll have coffee at exactly 3 classes? We would say this is the probability that x, which is the event of having coffee, equals 3. The number of successes we expect is 3. In calculator notation, at least on a TI calculator, this is binom PDF, binomial probability density function or distribution function. So I'm going to turn on my calculator. I'm going to clear everything. And here's what I'm going to do. I'm going to press second vars for distribution. Notice here it says binomial probability distribution. So again, that's second vars is distributions. And we're going to go down until we hit binom PDF. And with this operating system, at least, it asks us some questions. Number of trials, there are 5. Probability of success is 0.91. And the x value is the number of successes. So I'd put in 3, and I'll hit enter a couple of times, and it will just work it out for me. The probability of exactly 3 classes with coffee is 0.0610. So about a 6.1% chance. What's the probability that he'll have coffee at most 2 classes this week? So one way that we could do this is say, okay, let's find out the probability that it happens 0 times and add the probability that it happens 1 time and add the probability that it happens 2 times. And that's absolutely fine, but it's a little bit cumbersome. You could use lists to make it a little nicer. But the other thing your calculator will do is it will compute this directly. This is the job of a binomial cumulative function. Okay, so binom CDF does this. So I'm going to clear everything here. I'll hit second vars again to get to those distributions. And I go down and I find binom CDF. So this time I tell it once again, there are 5 trials, 5 days we're talking about. Probability of success is 0.91, and I put in the x value is 2. Binom CDF finds the probability of up to 2 successes. And we get that this is 0.00634, which seems really low, but remember, it's very likely that Ian will have coffee in class. So before we do the last question, let's just make some connections here. Exactly a certain number of successes is the job of binom PDF. At most, or we could think of that as up to 2 classes, is the job of binom CDF. Lastly, what's the probability that he'll have coffee for at least 3 classes this week? So in terms of notation, I would write this. Px is greater than or equal to 3. And I could do that with binom PDF. I could just find the probability that he has it at 3 classes plus 4 classes plus 5 classes. Binom CDF won't do this directly for me, but the slickest thing that you can do is say 3 or more, that is the complement of 2 or fewer. Okay. So this was a situation up here, 2 or fewer. 3 or more will just be 1 minus the probability of 2 or fewer. And we already found that. It was 0.634. And when I put that all together, subtract them out, I'll get 0.994, I think. Yeah. Very likely that Ian will have coffee at least 3 classes. You have another couple of pieces of information in your formula booklet about binomial distributions. One is the expected value, or the mean, is just n times p. So let's think about that. 5 times 0.91. We could multiply those two things together. We'll get 4.55. That means out of 5 classes, you expect Ian to have coffee at 4.55 of them. It's just the expected number that we'd run into. Okay? And of course, it means something a little weird when we talk about 0.55 of a class. We just follow the math. Variance, which is sigma squared, if you recall, is given by this, np by 1 minus p. Sigma, or the standard deviation, would just be the square root of that. Now, one little trick that you can do here is we've already found np. That was the mean or expected value, so that would be 4.55 times 1 minus p, which was 0.91. Maybe I'll just think about that as 0.09 and throw it in my calculator. It's a bit of an abstract idea, but what this is telling us is how large an unsurprising variation from the mean would be. Okay, so if you have Ian showing up with 4 classes out of those 5, then it's not that surprising. If it's more than 0.64 away from the mean, then it starts to be surprising. This leads into expected value. So expected value is essentially just the value of some outcome times its probability, and you sum up all of those. Expected value questions rely on both probabilities and some sort of quantifiable value, often money. So if we think about a game where a student rolls a cubical die, and if the die shows a 6, the student wins $9. If the die shows 1 or 2, they win $6, and if it shows any other number, the student wins $1. The expected value for a single play of the game is really sort of the average amount of money you'd win from one play. And the way you would find it is just taking the probability of that first event times its value, plus the probability of the next event, so it's a 2 in 6 chance of rolling a 1 or 2, times its value. And then finally times plus the probability of that last event times its value. And if we add all those up, that would be 1.5 plus 2 plus 0.5, so that's going to give us 4. In your formula booklet, E of x is given something like this. It's x, p, x equals x. What that is trying to tell you is just value times probability and add them all up. This leads to ideas of fairness. So the game costs $4.75 to play. Is it fair? There are 2 definitions you can take for fairness: that the expected value is the same as the cost to play, or that the expected value is 0 if that doesn't apply, if there's no cost to play. You can make it work so that it always works with the second definition, but right here, you expect to win $4 per game, and it costs $4.75 to play. It's not fair. The cost to play isn't equal to the expected return. And of course, all casino games are not fair if you actually go to a casino. The house always wins on average, and that's because it's set up that way. Ralph plays the game 30 times. How much money do we expect him to win or lose? Well, we don't know exactly what's going to happen to Ralph, but on average, we think he's going to lose 75 cents per play. So this will be lose 30 times 75 cents, or $22.50. That's a different kind of expectation right there. We can make some projections based on knowing what's going to happen on sort of the average game. Sample space is the set of all possible outcomes in a situation. It can be represented as a list, a tree diagram, or a picture. If you end up with a really difficult question that has sort of a finite but a kind of overwhelming number of possible outcomes, it can be helpful to just write them out. So I'll do an example with something that's fairly straightforward. If I flip 2 coins, I could have heads, then heads, or I could have heads, then tails, or I could have tails and tails, or I could have tails and heads. There it is as a list. Some people like to do it as a little grid. So first coin, second coin, there are the 4 possibilities represented as dots. Heads, 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 tails, tails, heads, and tails, tails. And the other one we've seen before, the tree diagram. And tree diagrams are great because you can work in the probability along with the sample space. So every final branch of that tree represents one of the 4 paths or the 4 outcomes we could have. Probability distributions in general have to follow a couple of rules. Every probability has to be between 0 and 1 inclusive. A probability of 0 means something is absolutely not going to happen. A probability of 1 means it's definitely going to happen. A probability of 2 means nothing. The sum of the probabilities of all possible events has to be 1 in a distribution. So we're going to do an abstract example down here. We've got a probability distribution, and we know that the expected value of this distribution is 2.46, and we have no context at all. So some things I can say are that these probabilities add up to 1. And I could clean that up a little bit. That's 0.54 plus A plus B equals 1. And that's not that helpful because we've got 2 variables and 1 equation. But if we had 2 equations, it might help us out a little better. So it's told us a second piece of information. The expected value is 2.46, which would be the probability times the value for each of these. 0.05 times 0. 0.22 times 1 plus 0.27 times 2 plus A is the probability of that outcome of a 3, and B is the probability of the value of 4. And now I can put all that stuff together. So 0.22 times 1 is 0.22 plus 0.27 times 2, that's 0.54. I'll just put them together here. That's 0.76 plus 3A plus 4B. And we know that that expected value is 2.46. One of the main reasons I'm doing this question is that somewhere in this set of videos, we have to have something that involves a system of equations, because it's likely to come up. 1 equation and 2 variables is no good. 2 equations and 2 variables, that gives us hope. And one way that we can solve these, and probably my favorite way, is through substitution. So I'll take what's going on the left-hand side, and I'll just rearrange this equation. I'm going to say A plus B equals 0.46, just move that 0.54 over, or A equals 0.46 minus B. And now that I know that, I can sub it into the other equation. 2.46 0.76 plus 3 times, instead of A, I can write 0.46 minus B plus 4B. And I can just keep working this through. And at any point, I could move that 0.76 over. Let's see. Multiply this out, I'll get 1.38 minus 3B plus 4B. Oh, glorious. We're just in 1 variable now. I can add 0.76 plus 1.38. I'll get 2.14. And this time it just says plus B. So I can move that 2.14 over to the other side, just subtract it from 2.46. I'll get B is 0.32. That's half of my answer, and it's more than half of my work. Lastly, I can go back to this A statement right over here and say, okay, A was 0.46 minus B, so that's 0.46 minus 0.32. A is 0.14. If I had time at the end of my exam, I'd make sure that that makes the probability distribution add up to 1 and gives me the correct expected value. But it is going to work out because we haven't done any arithmetic goofs. That brings us to the end of this first video on stats and probability techniques. What we're missing at this point is normal distribution, sampling techniques, and correlation and regression. So in the next video, I'll go over those things, as well as one classic question where the IB puts a bunch of probability techniques together in one biggie. I hope that you found this helpful. Good luck with the material, and take care, folks.